Imagine a star much smaller, cooler and redder than our Sun, TRAPPIST-1, an ultra-cool dwarf just under 40 light-years away. This proximity makes it a prime target for astronomers, as its light reaches us quickly, carrying secrets from a nearby system. Orbiting this faint star are 7 planets, all roughly Earth-sized, packed tightly encircling their star in days or weeks. The discovery of TRAPPIST-1 in 2017 electrified the scientific community, a rare chance to study a system with multiple Earth-sized worlds. The planets, named TRAPPIST-1b through H, cluster close to their dim star, with several, including TRAPPIST-1d, in or near the habitable zone. This system offers more than just one shot at finding a habitable world. It's a laboratory for understanding what makes a planet a home. By comparing these 7 rocky worlds, we can test our theories about planetary evolution and habitability. TRAPPIST-1 is a compact, nearby model of planetary formation, giving us multiple chances to search for life. Are we alone? TRAPPIST-1 doesn't answer that yet, but it's one of our best places to look. Studying these worlds helps us understand why one planet might be a paradise while its neighbor is a wasteland. The story of TRAPPIST-1 is the story of our search for ourselves, reflected in the dim, red light of a distant star. Among the 7 TRAPPIST-1 planets, TRAPPIST-1d stands out, right on the inner edge of the habitable zone. It receives a bit more energy than Earth, but not so much that it's immediately ruled out as temperate. This makes TRAPPIST-1d a critical test case. Is it a sweltering Venus, or did it manage to stay balanced and potentially habitable? The answer could redefine where we search for life in the universe. If TRAPPIST-1d avoided a runaway greenhouse effect, it expands the range of worlds that might be habitable. The James Webb Space Telescope, JWST, is designed to probe this question, using its infrared vision to analyze starlight passing through the planet's atmosphere during transits. This technique, transmission spectroscopy, lets us sniff the air of a planet nearly 40 light-years away. TRAPPIST-1d is a prime target for this investigation, helping us draw the line between living and dead worlds. The planet is a cosmic crucible, showing us the forces that shape planetary destinies. Is it a second Venus, or something more hopeful, a sign that Earth-like worlds are common? The data from JWST holds the clues, and scientists are piecing them together, one photon at a time. When we call a planet Earth-like, we start with size and mass. And TRAPPIST-1d is almost Earth's twin in size, at 98% of our planet's radius. This suggests it's rocky, not a gas giant, a world you could, in theory, stand on. But its mass is only about 30% of Earth's, making it much less dense. That hints at a different composition, perhaps more water or lighter materials than Earth's iron-rich core. Surface gravity would be about 60% of Earth's, affecting everything from geology to the ability to hold an atmosphere. Lower gravity means it's easier for gases to escape, raising questions about what kind of air, if any, TRAPPIST-1d has today. Temperature is the final key. Based on starlight received, its equilibrium temperature is around 15 degrees Celsius, close to Earth's average. But this is just a starting point. The real story depends on the atmosphere. A thick greenhouse blanket could make it scorching, while a thin or absent atmosphere would mean wild temperature swings. The numbers give us a sketch, but the atmosphere paints the full picture. TRAPPIST-1D's true nature hinges on what surrounds it. That's why every new observation is so crucial. The next step, uncovering the great atmospheric mystery. The fate of TRAPPIST-1d, habitable or barren, depends entirely on its atmosphere. We know its size, mass, and energy input, but without atmospheric data, it's like having ingredients without a recipe. The atmosphere distributes heat, shields from radiation, and creates pressure for liquid water. TRAPPIST-1d's atmosphere is the biggest unknown, and scientists are debating its nature using early JWST data. The planet's history matters. Its star's youthful flares could have stripped away any primordial air, leaving it bare. Or volcanic activity might have built a new atmosphere, if outgassing was strong enough. The composition of this blanket, if it exists, will decide the planet's fate. Every new observation is a clue in this unfolding cosmic mystery. Scientists see 3 main possibilities for TRAPPIST-1d's atmosphere, each telling a different story. First, a dead world, stripped of its atmosphere by intense radiation and weak gravity, leaving a surface exposed to space and wild temperature swings. Second, an exo-Earth with a moderate, life-friendly atmosphere, nitrogen, water vapor, and carbon dioxide, creating stable temperatures and possibly liquid water. Clouds could help regulate the climate, making this the world we hope to find. Third, an Exo-Venus, with a thick carbon dioxide atmosphere triggering a runaway greenhouse effect, boiling away any water and creating a scorching, uninhabitable surface. Each scenario is plausible, and JWST is our detective searching for the chemical fingerprints that reveal which path TRAPPIST-1d took. The stakes are high. Finding an Exo-Earth would be a breakthrough, while a Venus or barren rock would teach us about the limits of habitability. The answers are written in the starlight, waiting to be decoded. What we find will shape our search for life across the galaxy. The next step, diving deeper into these scenarios. Let's explore the Exo-Venus scenario, the most menacing possibility. Venus, similar in size to Earth, was transformed by a runaway greenhouse effect. Extra sunlight evaporated its oceans, filling the air with water vapor, which trapped more heat, creating a vicious cycle. TRAPPIST-1d, orbiting the inner edge of the habitable zone and receiving 14% more starlight than Earth, could face the same fate. If it started with water and a dense atmosphere, this extra energy might have triggered a runaway greenhouse, boiling away oceans and letting hydrogen escape to space. JWST would detect a thick carbon dioxide atmosphere and little to no water vapor, a clear sign of a Venus twin. Such a discovery would be sobering, showing that the habitable zone is not a guarantee of habitability. It would teach us about the delicate balance required for a planet to remain temperate. Even a world with the right size and water can become a sterile, scorching pressure cooker if conditions aren't perfect. This scenario would refine our search, steering us toward more promising worlds. The lesson: habitability is fragile and the universe is full of close calls. Now, imagine TRAPPIST-1d as an Exo-Earth, a true sibling to our world. It avoided atmospheric loss and runaway greenhouse, developing a moderate, stable climate. Volcanic activity could replenish its atmosphere with the right mix of nitrogen, water vapor, and carbon dioxide. Clouds would help regulate temperature, keeping water liquid and the climate mild. JWST would look for water vapor, methane, and carbon dioxide, potential signs of a habitable world. Finding an Earth-like atmosphere would be a historic discovery, transforming TRAPPIST-1d from a point of light into a real place. It would show that the ingredients for life aren't unique to Earth. Other blue worlds might be waiting among the stars. The third scenario, TRAPPIST-1d as a barren rock stripped of its atmosphere by its volatile star. It would resemble our moon or Mercury, silent, desolate, and exposed to space. Any water would be long gone, leaving a dry, cratered landscape. Atmospheric stripping by stellar flares and weak gravity could have left it airless. JWST would confirm this by seeing nothing, no atmospheric gases, just a flat, featureless spectrum. Even this sound of silence would be valuable, teaching us which planets can retain atmospheres around red dwarfs. Since red dwarfs are common, this knowledge is crucial for future searches. A barren TRAPPIST-1d would warn us that habitable zones around these stars may be more dangerous than we thought. Sometimes the absence of an atmosphere is the most important clue. Studying TRAPPIST-1d is about more than one planet. It's a pivotal moment in our quest to understand our place in the universe. Each outcome, Venus, Earth, or barren rock, teaches us about the boundaries of habitability and the power of stars to shape worlds. The James Webb Space Telescope pushes the limits of technology, analyzing faint light from 40 light-years away. The knowledge we gain will guide our search for life on countless other worlds. This quest is driven by the same curiosity that led our ancestors to explore the night sky. Exoplanets like TRAPPIST-1d are the new shores we're mapping, challenging our assumptions and expanding our perspective. As we await JWST's data, we're part of a grand scientific adventure. The story of TRAPPIST-1d will help write the next chapter in our cosmic story. Whether it's a paradise, a furnace, or a frozen desert, the journey itself is a triumph. For the first time, we have the tools to ask, are we alone? And we're closer than ever to finding out.